The silence across the abandoned German airfield was broken by a sound unlike anything Allied forces had ever heard. A low whistling roar that seemed to tear through the air itself, growing from a whisper to a thunderous scream as the sleek aircraft accelerated down the runway. American ground crews stood frozen, their eyes fixed on the machine that defied everything they understood about flight. No propeller spun at its nose. No familiar radial engine coughed to life. Instead, twin jets of blue flame shot from beneath swept wings, propelling the aircraft forward at impossible speed. April 1945. The Third Reich was collapsing, its armies retreating across a continent littered with the debris of Hitler's war machine. Allied forces advanced through Bavaria, overrunning airfields and industrial complexes that had once represented the pinnacle of German military engineering. At Lechfeld Airfield near Augsburg, American soldiers of the 7th Army moved cautiously through hangars still smoldering from hastily set demolition charges. They expected to find the usual collection of damaged Messerschmitts and Focke-Wulfs that had become familiar sights across conquered German territory. What they discovered instead would fundamentally alter their understanding of aerial warfare and mark the beginning of a technological revolution that would reshape military aviation for decades to come. Technical Sergeant Robert Hayes of the 358 Fighter Group was among the first Americans to approach the intact aircraft sitting alone on the tarmac. The machine appeared almost alien in its design. Where Allied fighters featured straight wings and conventional proportions, this aircraft displayed a radical configuration with wings swept back at sharp angles. Its fuselage was sleek and narrow, tapering to a pointed nose that housed no engine at all. Mastering to a pointed nose that house-striking were the two cylindrical pods suspended beneath the wings, their rear sections blackened by heat and exhaust stains. Hayes circled the aircraft slowly, noting details that contradicted everything he knew about fighter construction. The cockpit canopy was fully pressurized and sealed, suggesting this machine operated at altitudes no conventional fighter could reach. The landing gear was unusually robust for what appeared to be a relatively light aircraft. Stenciled markings on the fuselage identified it as a Messerschmitt Me-262, a designation that meant nothing to the American sergeant examining it that morning. Within hours, word of the discovery had reached intelligence officers who understood immediately what they were seeing. This was not simply another German fighter aircraft. This was the world's first operational jet-powered fighter, a machine that represented a quantum leap in aviation technology. The implications were staggering and terrifying in equal measure. Colonel Harold Watson, a veteran test pilot and leader of the Army Air Force's Technical Intelligence Operation, received the coded message at his headquarters in Paris. Operation Lusty, the systematic effort to capture and evaluate German aeronautical technology, had been searching for exactly this type of revolutionary aircraft. Watson assembled his elite team of pilots and engineers, men who had spent months tracking down Germany's most advanced aviation secrets. They called themselves Watson's Whizzers, and their mission was about to become far that arrived at more significant than anyone had anticipated. The team Lechfeld 3 days later included some of America's most experienced test pilots and aeronautical engineers. What they found exceeded their most optimistic expectations. Not only was the Me-262 intact and apparently operational, but German personnel who had remained at the airfield provided detailed technical documentation and offered to assist with evaluation procedures. The aircraft's former test pilot, Karl Bauer, explained through an interpreter that this particular machine had been prepared for a test flight when the airfield was abandoned. As American engineers conducted their initial examination, the revolutionary nature of the Me-262's design became increasingly apparent. The twin Junkers Jumo 004 engines represented technology that was years ahead of anything being developed in Allied countries. These were axial flow turbojet engines, fundamentally different from the centrifugal flow designs that British and American engineers were still struggling to perfect. The engines featured multiple stages of compressor blades that accelerated air through the engine core, where it was mixed with fuel and ignited in annular combustion chambers before being expelled through turbine stages that drove the compressor assembly. The sophistication of this propulsion system was matched by equally advanced aerodynamic design principles. The Me-262's swept wings were specifically configured to delay the onset of compressibility effects that occurred when aircraft approached the speed of sound. German engineers had solved problems that Allied designers were only beginning to understand. The aircraft's control surfaces included innovative slots and flaps that maintained effectiveness at the high speeds this machine was designed to achieve. American test pilot Captain Chuck Yeager, who would later become the first man to break the sound barrier, examined the Me-262's cockpit with growing amazement. The instrument panel was remarkably compact and efficient, displaying engine parameters and flight information with a clarity that surpassed anything in contemporary American aircraft. The gun sight was connected to an advanced ranging system that calculated target lead automatically, compensating for the aircraft's extraordinary speed. 4 30mm cannon were mounted in the nose, providing devastating firepower that could destroy heavy bombers with just a few hits. The decision was made to transport several captured Me-262s to the United States for comprehensive evaluation. The aircraft were carefully prepared for the Atlantic crossing, their systems documented and preserved with meticulous attention to detail. German technical personnel were recruited to assist with the operation, their expertise essential for maintaining these sophisticated machines during the journey to America. By July 1945, the first intact Me-262s had arrived at Wright Field in Dayton, Ohio, and Freeman Field in Indiana. American engineers began systematic testing procedures designed to understand every aspect of the aircraft's performance and construction. The first engine runs revealed both the promise and the problems inherent in this revolutionary technology. The Jumo 004 engines produced thrust levels that dwarfed any conventional aircraft power plant, but they also demonstrated alarming tendencies toward compressor stalls and flameouts that could disable the aircraft without warning. Test flights began with extreme caution. American pilots had to learn entirely new flying techniques adapted to the Me-262's unique characteristics. The aircraft accelerated faster than any Allied fighter, reaching speeds that made conventional combat tactics obsolete. At full throttle, the Me-262 could achieve speeds exceeding 540 miles per hour, making it nearly impossible for piston engine fighters to intercept. However, pilots quickly discovered that the engines required careful throttle management to prevent potentially catastrophic failures. The technical analysis revealed design brilliance constrained by wartime material shortages. The Jumo 004 engines incorporated advanced metallurgical concepts, but their construction relied on inferior alloys that limit a FSPAN TOD operational life barely 25 hours of flight time. Under ideal conditions with proper materials, these engines would have been remarkably reliable. Built with the resources available to Germany in 1944, they were engineering marvels held together by ingenuity and desperation. As testing continued through the summer and autumn of 1945, American engineers began to comprehend the full implications of what they were examining. The Me-262 represented not simply an advanced aircraft, but a glimpse into the future of military aviation. Its design principles would influence every jet fighter developed over the following decade. The breakthrough moment came during a routine engine inspection in September 1945. Chief Engineer Robert Stromberg was examining the Jumo 004's compressor assembly when he discovered something that would fundamentally alter American understanding of propulsion technology. The German engineers had achieved what Allied designers considered impossible. They had created an axial flow turbojet that compressed air through 17 stages of precisely angled blades, each stage increasing pressure while maintaining smooth airflow through the engine core. Stromberg called his team over to examine the compressor rotor. The precision of the blade angles was extraordinary. Each blade had been individually hand-finished to tolerances measured in thousandths of an inch. The metallurgy was equally impressive despite material limitations. German engineers had developed specialized steel alloys that could withstand temperatures exceeding 1,400 degrees Fahrenheit while maintaining structural integrity under extreme rotational stresses. These were not the crude materials American intelligence had expected to find in a desperate wartime project. The combustion chamber revealed even more sophisticated engineering. Instead of the single-can combustors used in early Allied jet engines, the Jumo 004 featured an annular design with multiple flame tubes arranged in a continuous ring around the engine centerline. This configuration provided more even heat distribution and eliminated the hot spots that plagued American experimental engines. Fuel injection was controlled through a complex mechanical system that automatically adjusted mixture ratios based on altitude and throttle position. Captain Eric Brown, the British test pilot who had flown more aircraft types than any pilot in history, arrived at Wright Field in October to evaluate the Me-262 alongside American test pilots. His first flight report would become legendary among those cleared to read classified testing documents. Brown described the aircraft as possessing flight characteristics that seemed to belong to a different era of aviation entirely. The takeoff acceleration was unlike anything he had experienced. Where conventional fighters required lengthy ground rolls and careful power management, the Me-262 seemed to leap from the runway with minimal effort. The twin jets provided thrust-to-weight ratios that made vertical climbs possible at speeds where conventional aircraft would stall. Brown noted in his report that the aircraft felt more like a rocket than an airplane during initial climb phases. At altitude, the Me-262's performance became even more remarkable. The aircraft maintained stability and control effectiveness at speeds where conventional fighters encountered compressibility problems that made them nearly unflyable. The swept wings delayed shockwave formation, allowing the aircraft to approach the sound barrier without experiencing the violent buffeting and control loss that characterized straight-wing aircraft at high speeds. However, the engines remained problematic. American mechanics documented failure patterns that revealed the fundamental constraints German engineers had faced during wartime production. The turbine blades were manufactured from steel alloys that lacked crucial elements like chromium and nickel, materials that Germany could no longer obtain reliably. Under sustained high-power operation, these blades would crack and eventually fail catastrophically. Engine replacement became a regular part of Me-262 testing procedures. American engineers calculated that operational squadrons would require enormous stockpiles of replacement engines to maintain even minimal readiness rates. Jumo 004 engine require each approximately 375 hours of skilled labor to manufacture, using materials and precision machinery that Germany simply could not provide in sufficient quantities during the war's final years. The weapon system analysis revealed tactical implications that troubled American strategists. The 4 Mk-108 cannons mounted in the Me-262's nose could fire 650 rounds per minute with devastating effect. Each 30mm shell contained enough explosive power to severely damage or destroy a heavy bomber with a single hit. The concentrated firepower meant that Me-262 pilots could engage Allied bomber formations with brief firing passes that minimized exposure to defensive fire. Mathematical projections prepared by Wright Field analysts painted a sobering picture of what might have occurred if Germany had deployed Me-262s in significant numbers earlier in the war. A force of just 300 Me-262 seconds, operating with adequate fuel and spare parts, could theoretically have shot down more Allied bombers in 6 months than were actually lost during the entire strategic bombing campaign over Germany. The aircraft's radar-assisted gun sight provided another technological revelation. German engineers had integrated early radar ranging with optical sighting systems to create targeting solutions that compensated automatically for the high-speed intercept profiles that jet fighters employed. American pilots testing the system discovered they could achieve hit probabilities that exceeded anything possible with conventional gun sights, even when engaging targets at relative speeds approaching 700 miles per hour. Intelligence officers studying captured German documents began reconstructing the Me-262's development timeline. The aircraft had first flown in 1941, powered by piston engines, before receiving jet propulsion in 1942. Mass production had been delayed not by technical problems, but by strategic decisions made at the highest levels of German leadership. Hitler's insistence that the aircraft be developed as a bomber rather than a fighter had consumed crucial months during 1943 and 1944. American engineers calculated that if Germany had focused solely on fighter production and deployment, operational Me-262 squadrons could have been engaging Allied bombers by early 1943. The strategic implications were staggering. Daylight bombing missions over Germany would have become prohibitively expensive in aircraft and crew losses. The entire Allied air campaign might have required fundamental revision. The testing program expanded to include combat simulations against captured American aircraft. Me-262s were flown in mock engagements against P-51 Mustangs and P-47 Thunderbolts to evaluate relative performance in realistic combat scenarios. The results confirmed German claims about the jet's tactical superiority. Conventional Allied fighters could not catch the Me-262 in level flight or climb. Their only advantages lay in superior maneuverability at lower speeds and much greater operational reliability. American pilots participating in these exercises reported psychological effects that concerned military planners. The experience of being repeatedly outmaneuvered by an aircraft that could engage and disengage at will created a sense of helplessness that had rarely been experienced by Allied air crews during the war. Fighter pilots who had dominated European skies found themselves completely outclassed by technology they had never imagined possible. The structural analysis revealed design principles that would influence American aircraft development for the next decade. The Me-262's airframe incorporated stressed skin construction techniques that distributed loads more efficiently than conventional designs. The wing structure used innovative spar arrangements that maintained torsional rigidity while minimizing weight. These techniques would appear in post-war American jets like the F-86 Sabre and F-84 Thunderjet. Wind tunnel testing of Me-262 components at the National Advisory Committee for Aeronautics provided data that advanced American understanding of transonic aerodynamics by several years. The swept wing configuration delayed shockwave formation and reduced drag rise at high subsonic speeds. American engineers realized that straight-wing designs they were developing for early jet fighters would be fundamentally limited in their performance potential. By December 1945, the testing program had generated thousands of pages of technical reports that would remain classified for decades. The conclusions were unanimous among participating engineers and test pilots. The Me-262 represented a technological achievement that had fundamentally altered the nature of aerial warfare. Its influence would extend far beyond military applications, establishing design principles that would shape civilian jet aviation and space exploration programs throughout the Cold War era. The captured aircraft continued flying test missions into 1946, providing American pilots with invaluable experience in jet operations before domestic jet fighters entered service. This practical knowledge would prove crucial during the Korean War, where American pilots flying F-86 Sabres would encounter Soviet-designed jets based on similar German technology, captured by advancing Red Army forces. The captured Me-262s arrived at Wright Field on a gray October morning in 1945. Their sleek forms shrouded beneath canvas tarps as they rolled off transport trucks. The secrecy surrounding Operation Lusty had reached its peak. Classified technical reports were already circulating through the highest levels of military command, each page stamped with warnings about the revolutionary nature of what American engineers were about to examine in unprecedented detail. Major General Curtis LeMay stood in Hangar 7 as the first Me-262 was wheeled inside, its swept wings catching the overhead lights in ways that seemed almost unnatural. The aircraft possessed an elegance that conventional fighters lacked, a purposeful beauty that spoke of engineering principles decades ahead of their time. LeMay had commanded bomber formations over Europe. He understood viscerally what this machine represented. In the wrong hands, at the wrong time, it could have decimated his fleets. The systematic evaluation began immediately. Teams of specialists converged on the aircraft from across the American aviation industry. Bell aircraft engineers examined the wing structure. Pratt & Whitney turbine experts studied the Junkers engines. Northrop aerodynamicists analyzed the swept wing configuration. General Electric propulsion specialists documented every aspect of the turbojet design. This was not merely military evaluation. This was industrial espionage on a scale never before attempted. Technical Sergeant Michael Romano, a veteran aircraft mechanic who had maintained P-51 Mustangs throughout the European campaign, approached the Me-262's engine bay with tools that seemed almost primitive by comparison. The Jumo 004 engine required completely different maintenance procedures from anything in his experience. Where radial engines used spark plugs and carburetors, the jet employed fuel injection systems and ignition chambers that operated at temperatures exceeding anything he had encountered. The engine bay itself revealed the sophistication of German engineering under impossible constraints. Every component was precisely manufactured despite wartime shortages. The fuel lines were routed with mathematical precision to ensure proper flow rates at all altitudes. The electrical systems used advanced connectors that eliminated the corrosion problems that plagued Allied aircraft operating in harsh conditions. Yet Romano could see evidence of desperate improvisation. Critical components were manufactured from substitute materials that would never have been acceptable under peacetime conditions. Dr. Theodor von Karman, the Hungarian-American aerodynamicist who had revolutionized supersonic flight, examined American understanding of the Me-262's wing design with growing amazement. The sweep angle was precisely calculated to delay shockwave formation at high subsonic speeds. The wing's thickness ratio varied systematically from root to tip, optimizing lift distribution while minimizing drag. These were not empirical design decisions based on trial and error. These were mathematically derived solutions to problems that American engineers were only beginning to understand. Von Karman's team conducted wind tunnel tests using scale models of the Me-262's wing configuration. The results confirmed what German flight tests had demonstrated. The swept wing design provided significant performance advantages at speeds approaching the sound barrier. American fighters with straight wings experienced severe buffeting and control problems at these speeds. The Me-262 remained stable and controllable throughout the entire speed range. The implications extended far beyond immediate military applications. Von Karman realized that commercial aviation would inevitably require similar design principles as passenger aircraft evolved toward jet propulsion. The fundamental aerodynamic lessons embedded in the Me-262's configuration would influence civilian aircraft development for decades. Airlines would eventually operate swept-wing jetliners based on principles first proven in this German fighter. The radar and fire control systems provided another technological revelation that stunned American electronics experts. The Me-262's gun sight incorporated early radar ranging with analog computers that calculated target lead automatically. This level of systems integration exceeded anything in contemporary Allied aircraft. The pilot could engage targets at relative speeds approaching 800 miles per hour with hit probabilities that conventional gun sights could never achieve. Captain Chuck Yeager, who would later break the sound barrier in the X-1, flew extensive test missions in the captured Me-262 throughout the winter of 1945. His flight reports described performance characteristics that seemed to violate fundamental assumptions about fighter aircraft capabilities. The acceleration was unprecedented. The climb rate exceeded anything achievable with propeller-driven fighters. Most significantly, the aircraft maintained excellent handling qualities at speeds where conventional fighters became uncontrollable. Yet Yeager also documented the engine reliability problems that had plagued operational Me-262 squadrons. During one test flight, the port engine suffered a catastrophic turbine failure at 25,000 feet. The engine literally disintegrated, sending turbine blades through the wing structure and starting a fire that nearly destroyed the aircraft. Yeager managed to land on the remaining engine, but the incident highlighted the technological constraints that had limited the Me-262's operational effectiveness. American metallurgists analyzing the failed engine components discovered the source of these reliability problems. The turbine blades were manufactured from steel alloys that lacked critical elements like chromium and nickel. Germany's strategic material shortages had forced engineers to use substitute alloys that could not withstand the extreme temperatures and stresses of turbojet operation. Under ideal conditions with proper materials, the Jumo 004 would have been remarkably reliable. Built with wartime substitutes, it remained a technological marvel held together by engineering brilliance and desperate improvisation. The weapons system analysis revealed tactical implications that fundamentally altered American thinking about air-to-air combat. The Me-262's 4 Mk-108 cannons could destroy heavy bombers with just a few hits. The concentrated firepower meant that jet fighters could engage enemy formations with brief firing passes that minimized exposure to defensive fire. Traditional fighter tactics based on prolonged engagement became obsolete when applied to jet versus jet combat. American pilots participating in mock combat exercises against the Me-262 reported psychological effects that concerned military planners. The experience of being repeatedly outmaneuvered by an aircraft that could engage and disengage at will created feelings of helplessness that had rarely been experienced by Allied air crews during the war. Fighter pilots who had achieved ace status flying conventional aircraft found themselves completely outclassed by technology they had never imagined possible. By spring 1946, the captured Me-262s had taught American engineers everything they needed to know about the future of aerial warfare. The sleek fighters sat silent in their hangars at Wright Field, their secrets extracted through months of meticulous testing and analysis. The technological principles embedded in their swept wings and axial flow engines would live on in American aircraft for decades to come. From the rubble of a collapsing Reich, American aviation had inherited the blueprints for tomorrow. The jet age had begun not with fanfare, but with the quiet hum of German turbines spinning in Ohio test facilities, forever changing the mathematics of flight itself.